I'm going to be talking about energy use today in pig facilities. This is something that actually one of the first items I worked on when I started in extension. I'm old enough to remember the last energy crisis we had in the 70s, and one of the first activities I did with extension was the solar demonstration project that we did in the late 70s and early 80s. So kind of what comes around goes around again. Anyway, so we're going to talk about energy usage, and I want to set the stage and say that I'll be talking about, when I say energy, I'll be talking about what I'm terming here direct or fossil fuel energy, and I think most of the people in the room here would talk about that. Now, Lee being a nutritionist and Yuzi and a few others, when they talk about energy, they want to talk about feed energy as well. And that is an important part of energy. Direct energy or fossil fuel energy use, primarily electricity and propane, is what's used. If you look at the total production of pigs from birth to market, and you add up all of the costs involved, it's really, energy costs are really pretty small percentage, anywhere from 3 to 5%, kind of depends on the time of year, etc. Where feed energy or feed costs, you know, from a producer, and those of you that raise pigs know this better than all of us, 60 or 70%. But this economic energy impact does affect some parts of the industry more than others. For instance, most of the pork that's produced today, there's a lot of people that are contract growers. Essentially, they don't own the pigs, they don't own the feed, they just build a facility. They get paid so much per pig to raise the animals, and they have to put up the bill for running the facility, principals and interest and all of that. And essentially, for those individuals, and at least I was good enough to work with a producer, and I'll show some of the numbers a little bit later, for that particular individual, he had a wean-to-finish operation, and his utility costs, electricity and propane, were actually 30% of his out-of-pocket costs. So that's actually some real money. So, all right. So present cost of fossil fuel energy, relatively stable cost. There is some variability due to location and generation, but you know, I think an average of 10 cents per kilowatt is reasonable. I realize some of you are paying more, some are paying less. Propane, that's probably the most volatile cost of any of our energy sources that we're using. But I'm guessing that $1.50 a gallon are probably in the ballpark. But propane can vary quite a bit of probably all the energy sources. I threw in diesel here. That's actually probably pretty close. It's probably a little high if you look at the off-road, over $2. There's a little less volatile cost in that involved, although we understand that the price of gasoline anyway varied a little bit more than expected recently because of some supply issues. Okay, area of electrical energy use in pig production. If we look at electrical, ventilation fans, both the exhaust fans, mixing fans, creep heat for young piglets, lighting, power washing, feed and water delivery. That probably covers 95% of the energy that's electrical use. Probably the largest use percentage in pig production is to run ventilation systems. Even if if you have some curtain-sided buildings, you might have some curtain controllers or circulation fans. But certainly in buildings that are mechanically ventilated, especially in the summer, you can have quite a bit of a lot of exhaust fans running that can be drawing quite a bit of energy. Moderate use are probably covered here in like creep heat and also lighting in buildings. You see here LED lights, and I'll talk a little bit about that, but I'm not going to talk a lot because you're going to have an expert, Scott Sanford is going to be talking from UW-Madison about lighting and efficiency a little bit later on. Smaller uses, delivering feed, water, that type of thing with relatively small motors. We don't have any, 20 horsepower motors typically like we do in grain drying or anything here for pig operations. Areas of propane energy usage, space heating, probably the biggest one, some creep heating, water heating for cleaning and washing. There maybe is a few that will incinerate baby piglets. That generally covers it. Major usage here, running propane, primarily propane, unless you're close to a natural gas line. Almost, I would say, 95% of pig production use propane. You're going to have space heaters like these hanging direct-fired, non-vented heaters. There are becoming a little more popular to have radiant heat systems, and a lot of those are propane-powered. So just if we look at finishing facilities, at least in the Midwest, I would say 90+% of them are what we would call either curtain-sided buildings or tunnel ventilated buildings. The tunnel ventilated buildings are 100% mechanically ventilated, ventilated year-round. In the summer now, all of the air exchange is done with exhaust fans. The curtain-sided buildings are essentially closed up and mechanically ventilated in the winter, but now in the summer curtains are open, and for the most part the wind is ventilating them. So certainly less energy usage or less fan usage there. These will have typically circulation fans to help move some air over the animals, however. So how much energy do we use in these facilities? And that information is not easily found or available, especially in certain parts of the country or up in this part of the country. This is some information that I got from a fellow extension person who was in the private sector, Bill Crawford, down in Fairmont, Minnesota. He actually works for a vet clinic and works with a lot of management systems, but he actually on the side owns this 2,400 head wean-to-finish barn himself, and he graciously shared with me his energy use values for 4 years, 2010 through 2013. And so you can just go ahead and see how much electrical energy and propane was used in that 2,400 head wean-to-finish barn. Now, for those of you that don't know the cycle, wean-to-finish are essentially, there's 2 turns. Those pigs will arrive in this facility at about 12, 14 pounds, 3 or 4 weeks of age, and stay there for the duration of the time until they're marketed. The propane use in wean-to-finish might be a little bit higher than in the grow-to-finish. Grow-to-finish, the pigs come in at 50 or 55 pounds. There's a nursery stage in the middle. So they might have a little higher energy usage because depending upon the time, you're having small pigs in this large buildings. But just reading down some of the information here, you can see we have fairly consistent from the year to year, and of course there's variation due to weather conditions. I just went ahead and calculated the energy uses per pig space. So this is basically adding up all that information and dividing by 2,400. So electrical, we can see right around 30 kilowatt hours per pig space for wean-to-finish operation. At least that's what I think was a pretty good average. And for propane, right around 2, maybe a little bit more than 2 gallons per pig space. Now, if we, my colleagues down in Iowa State, Jay Harmon, Mark Hanna, and a graduate student assembled some information that was presented at our professional meeting last year. And they collected some information, energy and propane use in swine finishing facilities. Now, essentially, they had a tunnel ventilated barn here, wean-to-finish, which was identical to the one that we just saw. And that number was pretty close to what we had before, 30 kilowatt per hour per big space. A little higher propane. So I kidded the Iowa folks. I said, "It's you're probably running your heaters a little bit too much, or some other things." As we'll find out, there can be you can use a lot more energy pretty quickly depending upon how things are managed. There are some other these other hybrid or curtain-sided barns using a little bit less propane and energy, and that's understandable because, again, they don't have as many fans, and probably they had larger pigs. They weren't putting those young pigs in. So this information kind of agreed pretty closely with what we had before, so I'm feeling fairly good about some of these estimates. Diesel energy, primarily I see that as in backup generators, and almost all of these facilities have to have those, especially ones that are mechanically ventilated. There's some use of, skid steer, tractors, etc. And actually, so, generator sets like this are real common and primarily are powered with diesel engines. Okay, now I'm going to run through just an estimate on energy use in a sow facility. And for those of you that are not familiar with pig production, essentially a sow facility will basically houses sows, and the product and what comes out of these sow units are these 12, 14 pound, 3 or 4 week old piglets that either go to a nursery or go directly into a wean-to-finish site. And 3,000 sow operation is a pretty common size. There's some that are up to 5,000, but this is a pretty common size operation. Now, I could not find data from one of these operations, and I think tomorrow, Eric is going to be talking about some energy collection from a sow operation. So we'll actually see how good my estimates are here. Again, operating fans, exhaust fans are probably a big energy electrical usage. You can have either heat mats or heat lamps that can draw quite a bit of electrical energy in a sow operation. There's a lot of different conventions. Conventional 250 watt heat bulbs, that although aren't used as much, there's some more energy efficient ones. But they're still used, and some people management-wise like pigs are drawn to light and prevent lay-ons and etc. But you are seeing a lot of electric heat mats used instead of the heat lamps, or at least the heavier ones. There are some propane fire radiant heaters though that are used. Lighting. This area in swine production is important, especially for sow housing. It has something to do with basically when sows cycle. I think most of the facilities that are operating today probably have fluorescent lights, although LED lighting is coming in. There is certainly a movement to that, and we certainly we'll see more of that. And here is a comparison with the different lighting. As I said, Scott is going to be talking about this, so I'm not even going to get into the description. No, the bottom line is here, LED lighting is really much more energy efficient, lumens per watt. It's really is much more efficient. Although they certainly cost a lot more, they last forever too. You don't have to change them. So I'll leave that to the discussion that Scott will have. So if we add up all of this estimated, and I made some estimates on the energy that's used in these sow operations, I came up with about 250,000 kilowatts total for running ventilation fans in a 3,000 sow operation. Creep heat almost about the same amount, which kind of surprised me a little bit when I just estimated it, but there's a lot of farrowing facilities, and they do use some energy. And land lighting can add up 170,000 kilowatt hours. So a little bit for power washing, feed, and water delivery, and I just came up with a little less than 700,000 kilowatt hours in a cell operation. If we do the same thing for propane, space heating again is primarily where you're going to use a lot of propane in a cell operation. Some for water heating. There is a need for hot water, and that'll take some energy. Estimating here about 37,000 gallons. So if we do the same thing for the sow operation we did for the pigs and put it on a per sow space, I came up with an estimate of about 230 kilowatt hours per sow space and a little over 12 gallons per sow space of propane. So as I said, of course there's a lot of room, depends on a lot of variation, but this gives us some place to start. Okay, maybe more importantly, I'll spend the rest of my time here just talking about how do we control some of these costs. Even though, as I said, they're relatively, when you look at the big picture, fossil fuel usage, relatively small percentage compared to feed use, but it is something that actually people can control, and it, as I will kind of get into, it's kind of easy to waste some of this energy through maybe mismanagement of ventilation systems or sizing of heaters, et cetera, et cetera. So a few things that I've listed: precise control of ventilation rates. Really important not to overventilate, because you're going to really up your fossil fuel energy use quickly. You want exhaust fan efficiencies. You want exhaust fans that are energy efficient, and we have the capability to select fans that can do that. We need a well-insulated structure, and we need tight buildings. In other words, that we don't have a lot of leaks in, so we can accurately control airflow. This whole idea of ventilation controllers or environmental controllers that operate our ventilation systems are great instruments, but if they aren't managed right, they can really cause a lot of energy usage. Energy efficient exhaust fans, we want a high CFM per watt rating, especially for fans that run all the time. When you select fans, you can essentially, you buy fans based on rating systems, how much airflow they have against a certain static pressure. But the second most important thing is this energy efficiency, CFM per watt. There can be quite a difference in that, the number for certain types of fans. Just an example, this is from the fan rating systems out of the University of Illinois called the Best Lab. They rate almost all of the fans that are used in livestock ventilation systems. These are 4 24-inch diameter blade fans. If you look at them from the front, you couldn't tell them apart, but they actually do perform quite differently. These are the CFM, cubic feet of air per minute rating for those 4 fans. You can see these top 3 are fairly good. The bottom one is considerably less. But over here, we can see these first 2 deliver almost very similar amounts of air, but this second one here has a lot more higher energy efficiency than the other one. If we would take those 2 fans and put them in a building and run them for say 5,000 hours a year, that most efficient fan would probably save us say at 10 cents per kilowatt hour. That costs us a little over $200. This other one would cost us almost $300 to run. So there's like $80 difference, and so that's each year. Even in a couple of years, you can probably recover the cost of that better quality fan. Large exhaust fans, belt-driven fans, especially these tunnel ventilated barns where we're moving a lot of air, and they're probably the most efficient system as far as CFM per watt. But one of the problems we have seen with these is that these belt-driven fans, the belts aren't tight and they'll be slipping. We did some data where we collected in-house measurements of a fan like that. This is a fan, 48-inch diameter fan. Should be rated up here. This is the best lab rating. When we checked it, it was down here. We were only operating at about 10,000 CFM, where it should have been operating at about 20,000. When we tightened the fan, we got up to 17 or 18,000 CFM. So that was certainly, we need, well-managed systems. A lot of belt-driven fans now are kind of self-tighteners, but it's something you still need to check on. Fans that are dirty or dusty, one of the first things I did was when I joined Extension, we actually rated some dirt, how much effect dirt had on fans. We found 40% reduction on airflow if shutters and grills were full of dirt, and that's can really make a big difference. When you buy fans, I know a lot of you probably don't pay a lot of attention, but you'll see these extra attachments on fans. These hoods will probably reduce the airflow from a fan. Here's the rating for just the shutters and the guards for a fan. The red line is kind of the standard. If you put a hood on it, they'll be down here. You lose about 10% of the airflow because it has to essentially change direction 90 degrees. However, if you put one of these discharge cones, and you'll see that on there, you actually enhance the flow rate of the fan 10 to 15%. So that's why you're seeing these discharge cones on most of the fan, because it actually increases the air delivery of those fans. So if you've got those, you want to make sure they're operating clean, not cracked or broken. I'm going to just do a little bit of a summary here, and I think this will be followed up later by what Lee's going to be talking about, temperature, how important the temperature is going to be. This is from Jay Harmon at again, Iowa State. He ran through this example, 1,000-head nursery and standard barn, well-insulated walls, ceiling, minimum airflow about right where we recommend, and using a 76-degree average room temperature. And if you have $2 propane, estimated propane for this barn is be about 1,000 gallons a year, or about $2,000. Just to show the importance of temperature, we set up a little table and say, here's our baseline at 76 degrees. Let's say for whatever reason you wanted to run that 4 degrees warmer, 80 degrees. Well, that's going to cost you another $700 a year. So it can really have an effect. If you wanted to run it cooler, you can save almost $600 a year. So you say, oh, how can you do that? Well, you could do that by running the air temperature cooler and putting in some radiant heaters. And this is a pretty common thing like you see in a wean-to-finish barn. You got these little pigs in there, put some mats down, and you have radiant heat. It might be 70 degrees in the room, but it's like 80, 85 down where the pigs are. So that's a good way to zone heat and save some energy. Okay, adding insulation in barns. Does it pay? The recommendation is R30 in ceiling, actually R20, or that's even pretty high in the walls, and then some perimeter insulation. Again, Jay Harmon from Iowa State borrowed some of these from him. He said actually improving, if you went from R30 to R40 in the ceiling, made it like a home, you'd probably only save $94 a year in that. If you only had R10 in the ceiling and went up to R30, you'd save $800. So adding insulation is most beneficial if it's poorly insulated. Making good insulation better doesn't really pay. We have to remember in livestock barns, we insulate primarily to prevent cold surfaces and condensation. Here we see a 6-inch knee wall, maybe a concrete knee wall like in a finishing barn, without any insulation at all, pretty low R value. If it's 0 outside, 70 inside, it's going to be 34 degrees or pretty cool in that inside surface. And when it's that cool with pigs inside, you're going to have condensation. In fact, if it was a little colder outside, we wouldn't have condensation, we'd have frost. Okay, and the best, by just putting in an inch of rigid foam insulation here, we warm that surface up big time and prevent any condensation. Now, certainly we prevent heat loss, but really the major reason we insulate livestock barns is keep surfaces dry. We also need to seal up any curtain openings or keep our barns tight. We want to have air coming in through design openings, not through the leaks. A lot of times in curtain-sided openings in the wintertime, they'll put plastic or put this bubble wrap. And these two slides are from Mike Brum, who we work with, Mike's former University of Nebraska swine extension person. Now he has his own consultant service down in Mankato. But these can really work well, tighten up these curtain, especially curtain-sided barns or even the tunnel ventilated barns. I'll finish up and talk a little bit about the controllers. Not going to get into a lot of discussion here, but I think there's a couple points I want to make about controllers. They're really excellent ways to control our temperature, our fans, our inlets, and our heaters, so they aren't fighting against one another. One thing I see a lot, they talk about a set point. You set the temperature on the controller, and everybody thinks that's the temperature it's going to be operating at. Actually, no, it isn't. It's just the target temperature. And at a certain time, you'll see the actual room temperature vary, and you want it to kind of move over time. Let's say this is maybe 2 hours, this 3 hours. It'll kind of meander like that. That's the way the system should work. If you have a couple of variable speed fans and single speed fans, this is kind of how the setup is. You'll say your set point is down here at 70 degrees, and it's in the summertime. You're going to be operating, when all 4 fans are operating, you're going to be operating probably at 77, 78 degrees up here. So that's actual room temperature, because you need every 1 or 2 degrees bandwidth, the differentials here between these setups, so you have time for the barn to respond, not having fans come on and off real quickly. Now that said, on the heat side, we can really run into problems, because here we got our set point, and now we're going the other direction. So we'll have heater come on at a certain temperature below the set point, maybe 2 degrees or 1 degree. It will then basically come on and run, and then the heater will shut off. But what happens, because a lot of times heaters are too large, the room will continue to heat and drive it past the set point and turn on temperature controlled fans. Okay. So if you don't have enough difference in here between what we call heater offset and differential, you can get this flipping back and forth. Heater runs, turns on the exhaust fans, then it gets cooler, heater on and off. And what you end up with, and we say, so to prevent this overshoot, we want at least a 1.5 degree difference between that. And what can happen is you end up temperatures like this, and this is again from Mike. This is in a matter of about every 3-4 minutes we get up, down, up, down, up, down, and that's not very comfortable for the pigs, and you're using a lot of energy that you shouldn't be using. So in this particular case, the set point was 70. Furnace came on at only 1 degree below it, was off at the set point, and then basically variable speed fans came on at 70.5. So it was, heaters are running, shutting off, the other fan came on, cool it down, up and down, up and down. So that's something we want to avoid. In this particular case, we need to turn that heater on down here at 67 and have it off at 68.5, so we have at least an offset of a 1.5 degree from the set point temperature. So those are little things that are really important when it comes to using Finally, most of the heaters that I see in livestock in pig barns, these LB whites or hanging heaters, almost all of them are oversized. Okay, most of the time farmers need much smaller heaters. And of course, the reason that you buy a big heater is because they're the same price as a small heater. So, you know, just like I had an old neighbor that would walk around and buy a winter coat that was like size 55 or something. He would wrap around it twice, you know. And I remember my dad asking, "Why did you buy such a big jacket?" Well, he said, "You get more for your money that way." Well, the same thing is kind of the heaters. If a 60,000 BTU heater is $200, or say $500, a $250,000 heater might be only $100 more. So you naturally buy that big one. But these big heaters are a real problem because they deliver too much and really promote this overshooting. So fortunately, most of these heaters have what's called a blue valve that you can basically cut back, and it reduces how much heat that heater outputs by 65%. So you actually can, this 250,000 BTU heater will operate more like 160,000 or 165,000. And I know anytime I have been in, and I know Mike gets into a lot of these barns, he always turns these down, and he said he's never had a farmer turn it back on again. They're always, they're usually always too much. So with that, I'll take any questions.